This is Chapter 5 in a nutshell review. We're looking at algebraic expressions here. So I'm looking at this 4m minus k. I want to go through a couple pieces. First of all, the m and the k are what we call variables. They either represent an unknown or something that will be changing. So the letter is what makes it algebraic, the variable. The 4 is a number being multiplied by a variable, so that 4 is called a coefficient. And if you had just a number, maybe if we had a plus 7 or something like that, then that number by itself is called a constant. So we have variables, we have constants, we have coefficients, which are the number being multiplied by a variable. So right now this thing is called an algebraic expression. A lot of what you're going to be doing is substituting to solve at this point. We're not solving algebraic equations because there's no equal sign. What I want you to remember is that when you substitute in, so I know what m is worth, it's worth -3. Make sure you put it in parentheses because otherwise it looks like this and doesn't, the bottom one look like 4 minus 3, but it's really 4 right next to -3. And then minus 5. So when I substitute in, this is what it looks like. Then I just do order of operations. I'll probably do leave, change, opposite. I have to multiply before I add, so one negative makes that negative. And now they're on the same team, so I add and use that same sign. And all we've done is we've plugged in what the variable is worth each time and then solved it. Here I have a couple of what are called arithmetic sequences. That means we're adding the same thing each time. You can always find that just by subtracting each one to see if you happen to be the same thing. So if I subtracted these, I'd get 3. Subtracted these, I'd get 3. So that one, the constant rate of change is 3. And one thing we want to be able to do is to extend that. So I could tell you the next number is 14 and 17. And we could keep going like that because I'm just adding 3 each time, if that makes sense. And then we want to be able to do a couple other things. I want to recognize that constant rate of change. And then I want you to get used to understanding this equation. This is called slope-intercept form of a line. Y equals mx plus b. And the slope, the constant rate of change, is the m. So I would start writing that as y equals 3x. But if it were just 3x, then whatever place it was in the sequence would be just take it times 3. But if I took 1 times 3, I wouldn't get to 5. Something else had to happen. So I took it times 3. Then what adjustment had to be made to get up to 5? Wouldn't they have had to add 2? Now that should be the equation that should work every time. So if I put in 2, 3 times 2 is 6. What's 6 plus 2? 8, just like we thought. And 3 times 3 is 9, plus 2 is 11. And 4 times 3 is 12, plus 2 is 14. And this now works for anything, so you could jump to like the 500th term. If you wanted the 500th term, you just put 500 in for x. 3 times 500 is 1500, plus 2 is 1502. So this plus 3 tells you how to get to the next term, but this y equals 3x plus 2 tells you how to get to any term instantly. Let's try that with the next one. So I could subtract to find out what they're adding each time. When I subtract these, I'm getting 7 and 7. So the constant rate of change, or the slope, is 7. Now, we could always check these to see if they're proportional, right? If I put the number of term in the sequence, that 2 is the first term in the sequence, that 9 is the second number in the sequence, that 16 is the third. I could just divide them. Like 2 divided by 1 is 2, 9 divided by 2 is 4.5, so they don't match. Remember, that's how you check to see whether something is proportional. Y divided by x, it was not proportional. That means that we're going to be adding something here. So, again, how I like to do it is I just take 1 and I replace it in. And I'll show it to you just a little bit different way, but what I'm doing is I'm putting in 1 right here, and I'm getting out 2. So my input is 1, my output is 2. Well, they took it times 7, so now I'm at this, but that can't be true. So what had to happen right here? They had to subtract 5. That makes this minus 5, so y equals 7x minus 5. Let's check it to make sure it works. If I put in 2, 2 times 7 is 14. 14 minus 5 is 9. If I put in 3, 3 times 7 is 21, minus 5 is 16. So there you have it. Remember, to get to the next term, you just add 7. That's where we get this. So the next number would be 23, so on and so forth. If you want to get to any term, you write this equation. And now if you wanted the 1,000th term, 1,000 times 7 is 7,000. minus 5 is 6,995. All right, this is kind of old information, but a quick review. These are the properties of operation that we want to talk about. What you notice in this first one is the order change. That is called the commutative property. It works for both addition and multiplication. So this could have been 7 plus 4, which is 11, 4 plus 7, which is 11, or 7 times 4 and 4 times 7. If you switch the order, that's commutative property. This one, the order doesn't change. It's 3, 9, 1, 3, 9, 1. But what changes is the grouping. The friends, or the group, the people that associated, or the numbers associated with each other were 3 and 9, and now it's 9 and 1. So in order of operations, we do the grouping symbol first, but if it's all addition, it doesn't matter. Also, if it were all multiplication, it would not matter. These two work, commutative and associative, for addition and multiplication. The next one is called the distributive property. This is an important one. I can't do the stuff in here because these aren't like terms, but I can get them out of there by multiplying the entire group by 5. I'm distributing that times 5 to the 7k, which gets me 35k. And I'm distributing it to the 1, which is then 5. I've got them out of jail, and I've distributed that 5 to them. The next two, these are called the identity property. Anything plus 0 is still itself, and anything times 1 is still itself. It doesn't change it if you add 0 or if you multiply by 1. This is called the 0 property. Anything times 0 is not 9, it's 0. I don't know why I wrote that. 9 times 0 is 0. Anything times 0 is 0. And then these are called the inverse properties. Anything times its reciprocal gets you back to 1, and anything plus its opposite gets you back to 0. That's why this, the reciprocal is also called the multiplicative inverse because it undoes it. And this is also called, the opposite is also called the additive inverse because it undoes it. And why would you want to get back to 0 and 1? Because then you're getting back to its identity, because anything plus 0, and if you're in addition, you want to be at 0. Anything plus 0 is itself. And if you're in multiplication, you want to be back to 1, so anything times 1 is itself. That gets you back to its identity. We use those properties to help us simplify. So there are 3 steps that you're going to take to simplify before you, eventually the next chapter will solve these things. But you want to do leave change opposites, so let me do that. Any subtraction we can take care of. Distributive property, we want to bust stuff out of jail, because really this negative 4k and this 7k want to be together, but I like to consider these parentheses like jail. So right now that stuff's trapped inside, and the only way to get it out is with the distributive property. So 2 times 3 is 6. 2 times negative 4k is negative 8k, and then we put the symbol back in between them. And then finally, combine like terms. I'm going to rewrite this whole thing so you see it. Problem is they're in the wrong order, and that's why we use things like the commutative property, knowing that since it's all addition, I can move things around. So I'm going to basically move this thing, these k's, over with these k's. They are like terms because remember, like terms have the same variable to the same power. K's match k's. So I can combine them. I have a 7 and a negative 8, so I have a negative 1 of those k's. And then I'm going to move this 6 over with this 10. Again, I'm using the commutative property to get 16. And when I combine this stuff, I get negative k plus 16. And then I ask this all the time in the class. This is 2 terms. Remember, terms are the things that are added together. So here's a variable term, negative k, and here's a constant term. There's 2 terms. The constant is 16. The coefficient is an understood negative 1, and the variable is k. And beyond that, we can't solve that. Here we go again. Leave change opposite, distributive property. That takes care of all that. Now combine like terms. Do g's match g squareds? No, they do not. So these 5g squareds have to stay separate, and these 6g's have to stay separate. The only thing that really combines are my 2 constants. I'm using the commutative property to get them together. 7 plus negative 2 is 5. This time, when I'm done, I have 3 terms. Here's my constant term, 5. My variables are this g and this g squared. That 5 is a coefficient, that 6 is a coefficient, and you're not able to solve it at this point. This, by the way, is called adding and subtracting linear expressions. So I'm going to show this one different way. Notice you have 2 things being subtracted here, so you can line them up, and then just make sure you have them in the right order. You can use your properties to get them in the right order. I just need to be careful because I'm subtracting these. So when I go to subtract them, I'm really doing a negative 3, because I would do leave change opposite, minus 9. Well, be careful, minus 9 is plus a negative 9. That becomes a negative 12. And I'm doing 5m minus 8m, be careful, plus the opposite, negative 3m. So again, your answer is negative 3m plus negative 12. You have two terms. There's your constant term, negative 12. Here's your variable term, because the m is the variable and the negative 3 is called the coefficient. And you can't solve it beyond that. But that's another way to do it, is to line up your things that match your like terms. M's match m's, and constants match constants. So line them up, and you can subtract or add them up and down. All right, the last skill in this chapter is on factoring. And factoring means to write something as a multiplication problem. So we want to write what we have here, this addition problem, as a multiplication problem. I like to think about factoring, especially of linear expressions or expressions like this, as reversing the distributive property. In other words, I see that these two things have something in common, so I want to divide that thing out that they have in common. So I'm going to remind you how to factor. Factor is writing it as primes, so I could be saying, well, I noticed that this could be g times 42, and then 42 could be broken down to 2 times 21, and then that could be broken down to 3 times 7. So those are the factors. If I broke down 24, that could be 2 times 12, which is 2 times 6, which is 2 times 3. A lot of times in grade school they do this with a factor tree, or sometimes they do it by dividing in a stacked way. They call this the cake method. But if you divide it by 2 and got 12, it's still not prime, so you divide by 2 and you get 6. It's still not prime, so you divide by 2 and you get 3. And now you have what is called the prime factorization, 2 to the third times 3. So if I look what they have in common, they both have a 2 and a 3 in common. Okay, so that means I can divide out a 6. So I'm going to take a moment and divide out a 6. So I've determined that the greatest common factor is 6. I'm going to divide both pieces by 6. So 42g divided by 6 is 7g, and 24 divided by 6 is 4. And then I put them in parentheses and put what I divided out. I divided out as 6. So now I've written it as a multiplication problem. 6 times the quantity 7g plus 4. And you can always check it by doing the distributive property, because 6 times 7g would be 42g, which is what I had. And 6 times 4 is 24, that's what I had. So we have factored that. Show you that again. We kind of did an easy one here that you can tell that 10 is the greatest common factor, so we're going to divide by 10. That means, remember, I'm putting the 10 outside here and I'm getting the thing that I get, the answer, the quotient, when I divide by 10. So I divide both pieces by 10. So 40 divided by 10 is 4. And 90k divided by 10 is 9k. And now I've written it as a product of 10 and the quantity 4 plus 9k. This is the factored form. And then, of course, we do the distributive property to bust them out of jail, so you can then move them around and things like that. So I call this the distributive property if I want to bust them out of jail, and then this is the reverse of the distributive property, which is the factoring that we're working on.